Hello friends, here in this video we will see a problem based on dual cycle. Here is the question. Now whatever is given in this question, I'll write that in the form of data. Now the compression ratio for a single cylinder engine operating on dual cycle is 9. So the first thing we can identify here is the type of the cycle, which is given as dual cycle. I'll write down the type. It is dual cycle. Then the compression ratio is given as 9. Compression ratio is denoted as R suffix C, and that is equal to 9. Next, the maximum pressure in the cylinder is limited to 60 bar. So P suffix max is 60 bar. So that is 60 into 10 raised to 5 Newton per meter square. Then the pressure and temperature of air at the beginning of the cycle are 1 bar and 30 degrees Celsius. So at the beginning the pressure is P1. It is 1 bar. So 10 raised to 5 Newton per meter square, and temperature T1 is 30 degrees Celsius. So 30 plus 273. Therefore we are adding 273 to convert degrees Celsius into Kelvin, and here this will be 303 Kelvin. Next, heat is added during constant pressure process up to 4% of the stroke. So it means, I'll write the statement as it is. Heat is added up to 4% of the stroke. Now this statement we would be using in the problem, that is in the solution part. Next, assuming the cylinder diameter and stroke length as 250 mm and 300 mm respectively. So the cylinder diameter is capital D, it is equal to 250 mm, and stroke length, which is denoted as capital L, that is 300 mm. Next, determine the air standard efficiency of the cycle. First question. So to determine the air standard efficiency of the cycle, this cycle is dual, so we have to find out the air standard efficiency for the dual cycle. Next, the power developed if the number of working cycles are 3 per second. So the second question is, power developed if the working cycles are 3 per second. So I'll write down number of working cycles is equal to 3 per second. Next, take for air, since the cycle we have here, it is also called as air standard cycle, wherein we are considering the working medium as air. So CV, specific constant volume, is given, and CP, specific constant pressure, that is given. So I'll write down the values, that CV is equal to 0.71 kilojoule per kg Kelvin, and Cp, specific constant pressure, 1.0 kilojoule per kg Kelvin. So now this is the question we have in front of us, and here if we see, the first thing we have to find out is the efficiency of the dual cycle. So with the data available, let us try to get the solution to this problem. Now in the solution part, the first thing will be to draw PV and TS diagram for the dual cycle. So in the solution, the first thing is PV, pressure volume, and TS, temperature entropy diagram. For dual cycle. Now the PV and TS diagram will be drawn in such a way that it is a graph PV is pressure volume, TS is temperature entropy. Now before drawing the PV and TS diagram, I'll mention the processes here. So the processes which take place in dual cycle are, now the processes are, first of all, process 1 to 2, it is called as a reversible adiabatic or isentropic compression. Second, process 2 to 3, it is constant volume heat addition. Process 3 to 4 is constant pressure heat addition. Process 4 to 5 is reversible adiabatic, which is isentropic expansion. At last, process 5 to 1 is constant volume heat rejection. So these are the processes in case of dual cycle, and these processes we have to show it on PV and TS diagram. The first process, reversible adiabatic or isentropic compression, will be shown on PV diagram with the help of a curve. So point 1 to 2, from point 1 to point 2, this represents the reversible adiabatic curve, or we can say the isentropic process, starting at point 1 and reaching up to point 2. After we have completed the reversible adiabatic, that is isentropic compression, as we can see here, during the compression process, initially the volume is V1, but after compression the volume is reduced and now it is V2. Then initially the pressure is P1. After that, once we have completed the compression process, pressure rises from P1 to P2 and volume decreases from V1 to V2. So this is the compression process. Next, during process 2 to 3, it is constant volume heat addition. So we will go on adding heat, keeping the volume constant. From 2 to 3. Here if we see, the volume of point number 2 and 3 both are same. So V2 is equal to V3. That is the constant volume heat addition. But pressure rises from P2 up to P3. Next, process 3 to 4 is constant pressure heat addition. So after constant volume heat addition, there is heat addition at constant pressure. From 3 to 4, and here if we see, the pressure of point 3 and point 4 both are same. So P3 is equal to P4. So this completes the constant heat addition process. After that, it is reversible adiabatic, or we can say isentropic expansion. So here we are having the reversible adiabatic or isentropic expansion, wherein we can say that, like it was during process 1 to 2, an isentropic compression process, during 4 to 5 it is isentropic expansion process. So both are following the same law, which is PV raised to gamma is equal to constant. That is the law for reversible adiabatic or isentropic process. Next, after the completion of the expansion process, we are having the last process as process 5 to 1, which is constant volume heat rejection. So for this constant volume heat rejection, I'll draw a vertical line from 5 towards 1, wherein the volume of point number 5 and point number 1, they are same. So V1 is equal to V5. So here is the complete PV diagram for dual cycle, and at point number 4 the volume is V4, and at point 5 the pressure is P5. Next, we can say that here there are two heat addition processes. The first heat addition is from 2 to 3, which is constant volume heat addition, QA1. During 3 to 4 it is constant pressure heat addition, QA2. Then during 5 to 1 it is heat rejection at constant volume, so that is Q suffix R. So now this is the PV diagram for the dual cycle. Next, I'll draw the TS diagram, and here, as the first process is reversible adiabatic, or the other word is isentropic, it is isentropic compression, so it will be shown with the help of a vertical line on TS diagram from 1 to 2. That is, the entropy will remain constant, S1 is equal to S2, but temperature rises from T1 to T2. So this is the isentropic process, which is shown on TS diagram with a vertical line, that is entropy remains constant but temperature rises. Next, process 2 to 3 is constant volume heat addition. For this, I'll draw a constant volume line from point number 2. Now this line which I have drawn, it indicates a constant volume, so V is equal to C. Next, as the heat is being added at constant volume, so during that heat addition process the temperature goes on increasing. So temperature will increase from point 2 up to point 3. That is, from starting from point number 2 up to point number 3, the temperature increases. Next, after constant volume heat addition, it is constant pressure heat addition. So for constant pressure heat addition, I'll again draw a line, but now during constant heat addition process, this line would be less inclined compared to the constant volume line, because constant pressure lines are less inclined as compared to the constant volume lines, and this can be proved with the help of one derivation which is not required in this problem now, but we have to only understand that the constant pressure line is less inclined compared to the constant volume line. So heat will go on adding from 3 to 4 following the constant pressure. We reach up to 0.4, and here as we see, the temperature has increased further from 0.3 up to 0.4. Next, after this, process 4 to 5 is reversible adiabatic or isentropic expansion. It can be shown with the help of a vertical line. Now, from 4 to 5, if we see here, S4 is equal to S5, that is entropy remains constant, but there is drop in temperature from 0.4 up to 0.5. The temperature drops. So this is the expansion process on TS diagram. Next, the last process is constant volume heat rejection, which we have shown on PV diagram. On TS diagram, again I'll draw a constant volume line like previously I had drawn. But the nature of this line should be such that both the constant volume lines, they should be of diverging nature. That is, the area should go on increasing, because constant volume lines are never parallel. They should have a diverging nature on TS diagram. So from 5 to 1, it indicates the constant volume heat rejection, wherein volume of point number 5 and 1 both would be same because they lie on the constant volume line. But as we see here, temperature decreases from 5 to 1 and even the entropy decreases. Then during 1 to 2, since it was compression, so there is work done during compression, which is work input to the system. During 4 to 5, we are getting the work output from the system, so it is work which we are getting in expansion. During 2 to 3 and 3 to 4, the heat is being added to the system. So since heat is added into the system, arrow is pointing inwards. So here we have QA1 as the first heat addition. The second heat addition is from 3 to 4. So again the arrow is pointing inwards. representing heat addition, and from 5 to 1 the heat is being rejected, so the arrow should point outwards, and this is the heat rejection. So here is the complete PV and TS diagram for the dual cycle. So now here, as we see in this problem, the diameter of cylinder and length of stroke is given. With the help of that, we are going to calculate the swept volume. Let us get started. Here I draw the diagram of that cylinder. Now here I'll mark the diameter of the cylinder. Next, these are the limits in which the piston can move. The upper limit, it is called as top dead center, TDC. At the bottom, here we have bottom dead center, BDC, and the distance between them is called as stroke length. Next, here as we see, once we know the diameter of the cylinder, from that we can calculate the area of this cylinder, and multiplying the area with the length of stroke will give us the swept volume. So swept volume will be in this location, the volume swept by the piston is called as the swept volume, and that will be equal to the area of the cylinder multiplied by the stroke length. Then whatever is there above the swept volume up to the cylinder head, this is the top cylinder head, so the volume which is there above TDC and up to the cylinder head, that will be called as clearance volume. And if we add clearance volume with swept volume, that is going to give us the cylinder volume. So here this much is called as the cylinder volume. So now we need to calculate all these values, that is of cylinder volume, swept volume, clearance volume, and everything here. In the data, if we see, the diameter of the cylinder and the stroke length is given. So I'll say that since the swept volume is given by swept volume, it is denoted by V suffix S, and it is equal to area of the cylinder, or we can say area of the piston, that is pi by 4 d square multiplied by stroke length L, so therefore putting the value of diameter and length, the diameter of the cylinder is given in the problem, it is 0.25 meter, so 0.25 square, into stroke length is 0.3 meter. So from this I am going to get the swept volume, and my answer is 0.0147 meter cube. Next, after getting the swept volume, now as compression ratio is given in the problem, and that compression ratio is equal to 9. So I am going to utilize this, that is, now since I'll write down, since compression ratio it is denoted as R suffix C, and that is equal to cylinder volume upon clearance volume so therefore compression ratio will become cylinder volume, as we can see here, it is swept volume plus clearance volume upon clearance volume, which is V suffix C. Now from this, here compression ratio is given in the problem as 9, so I'll put the value, therefore 9 is equal to Vs, that is swept volume, 0.0147 plus clearance volume is the value which we don't have, so I'll write down, that is V suffix C upon clearance volume Vc. So from this, therefore 9 into Vc, that is 9 Vc, is equal to 0.0147 plus Vc. Therefore on left hand side we have 9 V suffix C, on the right hand side we have 1 Vc, so I'll send it onto the other side, that becomes minus V suffix C is equal to 0.0147. so therefore 9 minus 1, that gives us 8 V suffix C. So finally V suffix C is equal to 0.0147 divided by 8. So hence my answer of clearance volume comes out to be 0.0018 meter cube. And now after getting the clearance volume, I'll calculate the cylinder volume, that is, since cylinder volume V suffix CYL is equal to swept volume plus clearance volume. Swept volume plus clearance volume is the total cylinder volume. So therefore the swept volume, we have found out it was 0.0147 plus clearance volume, that is 0.0018. So on calculating this, I'll get my answer of cylinder volume as, it is 0.0165 meter cube. So this is the cylinder volume, which is the total volume here, is what we have calculated. As we have drawn the PV and TS diagram, so I'll use the first process 1, to do reversible adiabatic or isentropic compression. Now how to move further in this problem? The thing is, if we look at the unknown, here the question is to calculate the efficiency of dual cycle first. So in order to calculate the efficiency of dual cycle, we need to know all the values of pressures and temperatures, because without having the pressures and temperatures, it is difficult to calculate the efficiency of dual cycle. If we look into the problem, only some values of pressures and temperatures are given, the remaining values we have to calculate. So to calculate the pressures and temperatures, I'll start with the first process, that is for process 1 to 2, which is reversible adiabatic or isentropic compression process. Now for this process, on the PV diagram we have shown that this curve, which is for the reversible adiabatic process, it follows the law PV raised to gamma is equal to constant. So I'll use this law for states, that is points 1 and 2, and I'll write down, therefore P1 V1 raised to gamma is equal to P2 V2 raised to gamma, and that is equal to constant for a reversible adiabatic process. Next, therefore I'll keep pressures on one side, so P2 by P1 on one side. Next, here I will be having V1 raised to gamma, in the denominator V2 raised to gamma. Next, gamma I can take as a common raised to power, so V1 by V2 raised to gamma. Therefore P2 is equal to, P1 will be shifted on the right hand side, V1 by V2 is nothing but RC, called as compression ratio, raised to gamma. Next, it is equal to, now if we look into the problem, P1 is, it is 1 bar, that is 10 raised to 5 Newton per meter square. So I'll write down the value as 10 raised to 5 Newton per meter square. Next, RC compression ratio is given as 9, and gamma value we can write it as 1.4. I'll mention in the bracket, assuming for air gamma is equal to 1.4. Next, therefore here I'll get the answer of P2 as 21.67 into 10 raised to 5 Newton per meter square. Dividing this by 10 raised to 5, that will give me 21.67 bar. So here is the pressure at point 2. Next, I'll calculate the temperature at point 2. For that, again in the same process, that is during 1 to 2, I can write down, since T2 upon T1 is equal to V1 upon V2 raised to gamma minus 1. This relation is for reversible adiabatic process, that is the isentropic process. So therefore T2 by T1 will be equal to, now V1 by V2 is nothing but RC, that is compression ratio. And why it is RC? Because if we look into the PV diagram, V1 is the cylinder volume and then V2 is the clearance volume. So V1 divided by V2, cylinder volume divided by clearance volume, that is equal to the compression ratio. So I'll write down, since RC is equal to V1 by V2 and the value is 9 given. Next, therefore T2 is equal to, now T1 value, it is given as 303 Kelvin. So I'll multiply with T1, that is 303. RC is 9 raised to 1.4 minus 1. Therefore T2 value comes out to be 729.6 Kelvin. So now we reach up to the second temperature and we have Here the process was 1 to 2. Next I'll use the second process, that is for process 2 to 3, which is constant volume heat addition. So here for states 2 and 3 we can write it as P2 V2 upon T2 is equal to P3 V3 upon T3, and again this will be a constant value for the states 2 and 3. Now therefore, since it is a constant volume heat addition process from 2 to 3, V2 and V3 will get cancelled out from both the side, as we can say, since the volume are same, V2 is equal to V3, and that we can even see it on the PV diagram, that volume at point number 2 and point number 3, they are same. Then after this I'll shift T3 on one side, so T3 will be on left hand side. Here I have P3 multiplied by T2 divided by P2 is equal to P3 value. Now if I look into the PV diagram, the pressure at point number 3, which is equal to the pressure at point number 4, this is the maximum pressure, and in the question here they had mentioned Pmax as 60 bar, so this Pmax will be P3 is equal to P4. So I'll use this value 60 into 10 raised to 5 Newton per meter square into temperature T2, which is, we have found out, 729.6 divided by the pressure at point 2, and pressure at point 2 we have calculated, it was 21.67 into 10 raised to 5 Newton per meter square. So therefore here the temperature at point number 3 will come out to be 2020 Kelvin. Then after reaching at this stage, that is constant volume heat addition, now I'll utilize one statement which they had given in the problem, that is heat is added up to 4% of the stroke. I'm going to use this statement, that since the heat is added up to 4% of stroke, and that is nothing but stroke volume. So if we see the PV diagram, on this diagram the heat addition starts at point 2 up to point 3, it is constant volume heat addition. Then from point 3 to point 4 it is constant pressure heat addition. So now here, as I have explained, that the heat addition starts at point 2 and ends at point 4, but we can take the heat addition as from V3 up to V4, because V2, the volume at point number 2, is equal to volume at point number 3. So I can say that actually if we see here, the heat is getting added at point number 2, but even if we take point number 3, that is, since V2 is equal to V3, we can write the relation in the form of volume. That is, I'll say that since the heat is added up to 4% of the stroke volume, I can write down, it means that therefore the fuel is cut off at 4% of stroke volume. So it means now if I see here at point number 4 the fuel is getting cut off, fuel injection or we can say fuel addition stops. So this is the fuel cutoff. Now I can write this statement in such a way that therefore V4, that is volume after the cutoff, that is V4, to the volume before cutoff, which was V2, and here I can even say V2 is equal to V3. So instead of V2 I'll write down V3, that is V4 minus V3 is equal to the fuel is cut off at 4% of stroke volume, and stroke volume is volume 1, that is V1 minus clearance, that is V2. So 4% of V1 minus V2. Next, therefore here I'll keep V4 minus V3 on one side. I'll shift V1 minus V2 in the denominator is equal to 4% 0.04. Therefore I'll write down here I am dividing the numerator and denominator by V3. So here V4 divided by V3 minus V3 divided by V3. So this is the numerator. In the denominator we have V1, so V1 will remain as it is, divided by V3 minus V2 divided by V3 is equal to 0.04. that is dividing the numerator and denominator by V3. Therefore V4 upon V3. So now here I have written V4 by V3. This V4 by V3 is nothing but it can be written as rho, which is called as the fuel cutoff ratio, minus V3 upon V3, that will get cancelled out and 1 remains here. So rho minus 1 divided by V1 upon V3. Now if we see here in the PV diagram, V2 is equal to V3. So if we replace V3 with V2, so it will become V1 by V2, and V1 by V2 is cylinder volume upon clearance volume, that is compression ratio. So this will be R suffix C, compression ratio, minus V2 by V3. Again, as V2 is equal to V3, so we can cancel them out and here 1 remains, minus 1 is equal to 0.04. Now from this we can get the value of rho, and here I'll explain that this rho since rho is called as fuel cutoff ratio, it is the fuel cutoff ratio, and it is equal to volume after cutoff to the volume before cutoff. Therefore rho will be equal to the volume after fuel cutoff. As we see here, when the fuel is cut off, the volume is V4, so it is V4, and the volume before cutoff, that was V2, or we can say equal to V3, so V4 upon V3, that is equal to rho. Now, so I'll calculate the value of rho here. Therefore, rho minus 1 is equal to 0.04. I'll shift RC minus 1 onto the other side. Therefore, rho minus 1 is equal to 0.04 into RC is 9 given minus 1. So therefore, here I'll get the value as rho is equal to, this entire term will be 0.32, and minus 1, if it goes onto the other side, that becomes plus 1, and my answer is rho is equal to 1.32. that is the fuel cutoff ratio. Next, this was regarding the second process, or now I'll take the third process, that is for process 3 to 4. It is constant pressure heat addition. So therefore, here we can write it in this way, that P3 V3 upon T3 is equal to P4 V4 upon T4, and that is equal to constant. Now, as the pressure is constant here, so P3 and P4 will get cancelled out from both the sides. Therefore, I can say that I'll shift T4 on one side, so T4 goes onto left hand side. Here we are having V4, T3 will be multiplied, so V4 into T3 divided by V3. Next, after reaching at this stage, I can say that V4 upon V3 is nothing but rho, which is the fuel cutoff ratio we have seen, into T3. Now I'll put the values. So therefore, T4 will be equal to, the rho value is 1.32 into T3 we have found out it was 2020 Kelvin. So from this I'll get the value of T4, and it comes out to be 2666.4 Kelvin. So here we have calculated the temperature of point number 4, and this will be the maximum temperature in the cycle, and that can be seen on the TS diagram as well, that the temperature of point number 4 is maximum. Next, I'll say that after this I'll use the process 4 to 5, which is called as reversible adiabatic or isentropic expansion. So here we can write down that the expansion ratio will be T5 upon T4 is equal to V4 upon V5 raised to gamma minus 1. This can be written for the isentropic process, because like compression was isentropic, even the expansion is isentropic. So I have written that T5 upon T4 is equal to V4 upon V5 raised to gamma minus 1, because temperatures and volumes, they are inversely proportional. Now therefore, here I can say that after reaching at this stage, I'll explain this small concept of V4 by V5, that since V4 upon V5, it can be written as, here I am multiplying since it is V4 by V5, so I'll keep them as it is, that is V4 here, multiplication, here there is V5, multiplying and dividing by V2. Next, after this, since I can say that V4 and here we are having V2, but V2 is equal to V3, so V4 upon V3 into V2 upon, instead of V5 I can write down V1, and instead of V2 I have written V3 because the volume was constant. So therefore I can say that V4 upon V5 will be equal to V4 upon V3, that is called as the volume after cutoff to the volume before cutoff. It is the fuel cutoff ratio. Next, multiplying by V2 by V1. See here, V1 by V2 was compression ratio RC. So V2 by V1 will be reciprocal, that is it will be 1 upon RC. So finally V4 by V5 will be equal to rho upon RC. Now once I know the value of V4 by V5, I can shift it here. So therefore T5 upon T4 value we have calculated 2666.4 is equal to, it is V4 by V5 is rho upon RC raised to gamma minus 1. So therefore T5 will be equal to, this term would be shifted, rho we have found out it was 1.32, RC is 9 raised to 1.4 minus 1, which is the value of gamma for air. Here T5 value comes out to be, on calculation, 1237 Kelvin. So now once I have calculated T5, I'll use again in this process 4 to 5 one more relation, like I'll write down also P4V4 raised to gamma is equal to P5V5 raised to gamma. This is for isentropic process. Now therefore we want P5, so I'll keep it on one side. So P5 upon P4, pressures would be on one side. Next V4 upon V5, I can take gamma as the common raised to power, then it is equal to, V4 will be as it is, instead of V5 I'll write down V1 raised to gamma. Since V1 is equal to V5, the volume is constant. Now P5 is what we have to calculate, so I will be keeping P5 on one side, P5 will be on one side. Next, we have seen that previously V4 by V5 is also equal to rho upon RC. So for this I can write down V4 by V5 is equal to rho upon RC raised to gamma multiplied by P4. So therefore P5 will be equal to, rho is 1.32, RC is 9, gamma is 1.4 into pressure at point 4, and we have seen that pressure at point number 3 is equal to the pressure at point number 4, P3 is equal to P4, and at P3 we are having the maximum pressure which is 60 bar, so it is 60 into 10 raised to 5. I'll mention that since P3 is equal to P4. On calculation I'll get the answer of pressure at point 5 as 4.08 into 10 raised to 5 Newton per meter square. Dividing by 10 raised to 5, I will get it in terms of bar. So 4.08 bar. So here I have calculated the pressures and temperatures at all the points. Now, if we look into the question, the first thing which they are asking is to calculate the efficiency of dual cycle. Now, in that efficiency of dual cycle, which is the first question, I'll write down that calculation of efficiency of dual cycle, that since the efficiency of dual cycle, it can be written by a general formula, that is heat added minus heat rejected upon heat added. This is the general formula. Also, the efficiency of dual cycle, heat added will be Q suffix A minus heat rejected will be Q suffix R, divided by heat added is Q suffix A. So finally, the efficiency of dual cycle will be equal to QA and QA. Here this will get cancelled out because this will be Q suffix A upon Q suffix A minus Q suffix R upon Q suffix A. So from numerator, from denominator, QA will get cancelled and 1 remains. So 1 minus QR upon QA is the formula to get the efficiency of dual cycle. So I will be keeping this as equation number A for us, and from this we will get the efficiency value. So this is the equation A. Now I'll go for the calculation of heat added and heat rejected. Now, therefore, total heat added is given by Q suffix A is equal to, if we see that the heat addition process is from 2 to 3 and 3 to 4, that is at constant volume, constant pressure. So the total heat added is given by heat added at constant volume plus heat added at constant pressure. So therefore Q suffix A will be equal to, the heat added at constant volume is M suffix CV into temperature change, and during the constant volume heat addition, temperature starts increasing from point 2 to 3. So highest temperature is T3 during the constant volume process, and it is the minimum temperature is T2. So T3 minus T2 is the temperature difference for constant volume heat addition. For constant pressure heat addition, it is MCP, specific heat at constant pressure, into the temperature change at constant pressure is from 3 to 4. So T4 minus T3. T4 minus T3. Therefore, here I'll say that assuming the mass as 1 kg, assuming mass M is equal to 1 kg, that is, we will calculate the heat added in terms of per kg basis. So therefore, if the mass is 1 kg, we are left with CV T3 minus T2 plus CP T4 minus T3, putting all the values. So CV value is given, it is there in the problem. For air, the Cp and Cv values were already given to us in the data, and if even we look at the question here, Cv is 0.71, Cp is 1, so Cv is 0.71. Next, temperature T3, it was 2020 Kelvin, minus T2 729.6 Kelvin, plus Cp value is 1, T4 is 2666.4, minus T3 is 2020 Kelvin. So on calculation throughout, I'll get the answer of heat added as QA is equal to 1562.58 kilojoule per kg, because we are getting the heat added in terms of per kg basis, as the mass is 1 kg which we have assumed. Next, I'll write down similarly heat rejected is given by Q suffix R is equal to, since the heat is rejected, it is heat rejected at constant volume. So we have heat rejected as mCv. The heat rejection is from 5 to 1. That we can see it from the PV and TS diagram. Heat rejection is from 5 to 1, so T5 minus T1. Here putting the values, mass is 1, Cv is 0.71 given, then T5 value is 1237 minus T1 is 303 Kelvin given. So therefore the heat rejected value will come out to be 663.14 kilojoule per kg. So once we have the heat added and heat rejected, we can easily calculate the efficiency of dual cycle. So now here we have found out the heat added and heat rejected. Next, I'll put these values in equation A to get the efficiency of dual cycle. So therefore put QA and QR, that is heat added and heat rejected, in equation number A. So therefore the efficiency of dual cycle will be equal to 1 minus, it is QR upon QA. So QR is 663.14 and QA it is 1562.58. So therefore the efficiency of dual cycle will come out to be 0.5756 or 57.56%, and this is the first answer for us. Next, after getting the value of dual cycle efficiency, next the question is to calculate the power developed, and it is given that the number of working cycles per minute is per second is 3. So after this I'll say that therefore for the calculation of power developed. Now in this, first we need to calculate how much is the work done during one cycle, and for that I'll calculate the value of mass, because it would be required in the calculation of power to get the unit of power in some form. For that I'll write down, since for state 1 P1 V1 is equal to mRT1, this is the characteristic gas equation. Next, using this we can find the mass. So therefore M will be equal to P1 V1 upon RT1. So here therefore M will be equal to, P1 is given in the question, it was 1 bar, that is 10 raised to 5 Newton per meter square. We have to be careful of the unit. While calculation of mass, put the value of pressure in terms of Newton per meter square, not in terms of bar, that we have to remember. Then V1 was the cylinder volume, the value was 0.0165 divided by R, which is the characteristic gas constant, and for air we can take the value as 287 joule per kg Kelvin, into T1, the temperature is given as 303 Kelvin, into bracket I'll write down, let R is equal to 287 joule per kg Kelvin for air. So therefore on calculation I'll get the answer of mass. It comes out to be 0.0189 kg. Now after getting the mass, I can easily calculate the work done, first of all per cycle. So therefore power developed is nothing but work done. So work done per cycle, it is equal to heat added minus heat rejected, and here we are going to multiply it by mass. So it is mass into QA minus QR, because previously this would have given us the unit as kilojoule per kg, but since here we are multiplying it with kg, so kg into kilojoule per kg, that will become kilojoule. So therefore the work done per cycle will be equal to, mass is 0.0189, heat added it was 1562.58 minus heat rejected 663.14. so therefore the work done per cycle value was found to be 16.99 kilojoule, because the unit is kilojoule as I have explained. At last we have to find out the work done or power developed for the cycle which is given in the problem, that is 3 number of cycles per minute per second. So therefore the work done, or we can say power developed, since the number of cycles are 3 per second, so work done or power developed for 3 cycles per second will be work done per cycle multiplied by 3, that is the total power developed, or I can write down the total work done as work done per cycle was 16.99 into 3. So therefore the total work done, or we can say in other words the power developed, it is 50.99. And here if to check the unit, first of all work done per cycle is having the unit of kilojoule, and this is 3 per second, so into it is per second, so 1 upon second, and kilojoule per second, that is nothing but it is called as kilowatts. So in order to get the unit of work done or power in terms of kilowatts, that is why we had used mass here to get the work done or power developed in the form of kilowatts, because kilowatts is the unit of power. So I'll say that therefore power developed is same as the work done, and the value is 50.99 kilowatts. This is our second answer, and with both the questions answered, we can say that the problem has been completed.